All right, so order, please.
That's a good way to start with a chair.
All right, so it's my pleasant duty to introduce Amit Einav from Durham University. He's going to speak of order and chaos. You have the floor.
Thank you very much, and I'd like to start by thanking the organizer for inviting me to this lovely workshop with this lovely community at this fantastic place. Invite me again. I love it. I am going to speak about, as the title refers to, about chaos and a bit of order in the framework of mean-field limits. Now, I know that half of the community here will completely understand what I'm saying right now, other half maybe a bit less. So I will spend a few minutes, 5 to 8, on just giving you the framework of what I'm talking about, mentioning Katz's model again, which was mentioned in, on Monday. So I think that it will take me 28 minutes. Just so you know in advance, I will steal a few more minutes. So this framework of mean-field limit, for me, started back with the seminal work of Mark Katz in 1956 and his particle model. Now, at that point, I am not paraphrasing, this is my imagination of what happened. I wasn't alive at that point. Katz really wanted to give a probabilistic justification to a very important fundamental kinetic equation, the Boltzmann equation. He just wanted to give some probabilistic justification. And after all, the Boltzmann equation is kind of probabilistic by nature. It's the evolution of an average particle in dilute gas. So he said, not really, but that's again my imagination. Let's consider some sort of an average model of n particles from which we are going to get the Boltzmann equation as a limit in some sense. Now, I'm not going to go too much into this model, and when I say model in this community or in general, what I actually mean is there is some jump process, probabilistic jump process that describes the evolution of the density, probability density of the ensemble, and that's what I want to explore. So don't think that I'm actually going to model or show you a numerical simulation. That's not going to happen. So the Katz process was, he considered n particle in the setting of having one-dimensional velocities for simplicity, and they undergo some collision that's timed by a Poisson stream clock. And when they collide, the ensemble itself, which is two particles from the ensemble, they collide, they scattered in a certain way. I'm going to go fast because Eric even wrote this in his slides. And we restart the process. The evolution equation for, oh, sorry, this is a drawing, not drawing, I use LaTeX to do this. I think this is one of the most impressive slides that I have here. So they collide, they scatter. It's in 2 dimensions, so it's a bit of a lie, but just to give you the impression of what's happening here. And the equation for the evolution equation for the ensemble of elements is given by that. We usually call this the master equation, a joke to Doctor Who fans, maybe not, right? Or the Liouville equation, depending how you like to think about it. And it really is a kinetic equation in the sense that there's a gain term and there's a loss term. I gain the possibility to be in a certain velocity ensemble by collision. So this is exactly, I'm choosing a random two elements to collide, and then the collision is with the scattering, and I gather it all up, and after the collision, I get the ensemble that I want. So this is how I can gain the possibility to be in a certain ensemble. And how do I lose it? Well, if I start with the ensemble of velocity I'm in, any collision up to a set of measure 0 will completely move me away from it. So that's why you get this minus I term, which you're used to seeing that in most kinetic equations. The factor n is there, and it's very important to make sure that in a unit time that's independent of n, we will see at least one collision. It will make something happen because, remember, n is the number of particles. I'm probably going to take it to infinity. I am going to take it to infinity. Now, how can I get from this Boltzmann equation? Boltzmann equation is an equation for an average particle, one particle in dilute gas. Here I have everyone. Yeah, it's not exact, but it's for the entire ensemble. So if I know the possibility to find the ensemble in a certain position statistics, then I'll just integrate everything out but one particle, and that will tell me what the evolution of one average particle in my system is. Now you might ask yourself which particle you need to single out, and my answer will be, well, if you want a probabilistic model, if you want something that's average, the particle should be indistinguishable. Otherwise, if they're all labeled, if we have Madalena and Jimmy and John and, I don't know, Jane, then I'm back to deterministic. Everyone has their trajectories. I don't want that. So they're indistinguishable, and as such, it doesn't matter which one I'm isolating. I'll isolate the first one. So I'm looking at the marginals. And when I'm integrating the marginal, and I'm looking at the equation for the first marginal, the average particle, unsurprisingly, I get that its evolution depends on its interaction with another particle, on the second marginal. My heart sinks. This is not a closed equation. How do I solve this? Well, maybe I'll compute the second marginal equation. I'll do that, and that depends on the third marginal. I can continue and say that and waste all my time, but I'd rather not. You can continue and create this hierarchy, which is known as the BBGKY hierarchy, but in the end, you're back to your original master equation, Liouville equation, and we're stuck. Now, by the way, I can write an explicit solution to this equation, but that's not the point. My point is I would like to see the dependency in the number of elements in my particles. I want to take n to infinity. I'd like to close this equation. And then, that was a fantastic idea by Katz. Up to this point, I didn't really use the idea that it's dilute gas. Now, I did use the idea that I have pairwise interaction, that only two elements appear in the collision. But I didn't really use properly the fact that it's a dilute gas. Now, because it's dilute gas, let's say now the second marginal means I'm focusing on these two particles and I'm looking at them very, very intently. And you continue to inject more particle to my system, and as you do that, you keep it dilute. But that means that these two particles have less and less chance to meet each other. As the number of elements in the system increases, they become more and more independent. So if somehow you tell me that an average particle stabilizes on some profile as n goes to infinity, if fn1 goes to some f of v, then I expect that these two particles that I'm looking at them, I'm not taking my eyes off, they decouple and their distribution becomes f times f as well. And if I look at 3 particles, the same. And if I look at 5 particles, the same. As long as I look at fixed amount of particles such that as I increase the particle in my system, they become less likely to meet, this will work. So if I'm looking at any finite marginal, I expect the diluteness would mean that as the number of particles increases, they will become independent. And this is exactly the notion of molecular chaos in our framework. And I think that Dimitri definitely mentioned that, and also Emanuele, I think, mentioned that on the first day. Now, Katz wrote it rigorously, and you see, if I have this asymptotic correlation, then I can go back to my equation, take n to infinity, and get a fantastic equation, which is a caricature of Boltzmann equation. We're all very happy, but I did lie. Because what I wrote here, this chaos idea, is a static property. It's a functional property. And I'm applying it to an evolution equation, a time-dependent equation. So what I really, really need, if I want to apply to the equation, is to show that this chaos propagates with the equation. If you start with chaotic states, as time increases, you always continue to get chaotic states. And that was the crux of Katz's paper in 1956. He showed that, he took the limit, we got the equation, everyone's super happy, you know, even 67 years later. I'm personally super happy about that. My point, however, at this point, forget about Katz's model. This is a general framework that you can do in order to try to understand the behavior of a limiting average element in many element system. The only thing that I've used in order to get this limit equation was I had an average model, i.e. an equation for the probability density to find many elements at a certain state, and I gave you an asymptotic correlation relationship, this was this chaos, that spoke about the emergent phenomena you expect to see. You expect that because the gas is dilute, things will decouple. They become independent. But you can expect many other things. I mean, in general, we're full of expectation. So if I combine these two things, this average model plus asymptotic correlation, I may proceed in the same way as long as I show propagation of this correlation, but let's leave that aside. I can get an equation for a limiting average element in your system under your assumption, which will then hopefully give you information on the system. And Boltzmann equation is super important. We've studied it 130 years after it was conceived. We're still studying it. It's very, very interesting. So this gives us tools to give justification and to find equation. This framework of having this average model and asymptotic correlation is what we call the mean field limit approach. And we, in the last 3 decades, possibly more, this idea permeated into well beyond just particle system. We have particle system equation that represent biological swarm, that represent chemotaxis, that represent social behavior like consensus model. We all do similar things to that conceptually. I've lost, here we go, here's my clicker. However, in all this various setting, almost to date, the only asymptotic correlation we use is chaoticity. We always assume the appearance of independence. And in many biological and sociological models, if we are going in a shopping center, while we are quite chaotic, eventually there will be formed some sort of a flow. So chaos doesn't seem to be always the right choice. And indeed, in a series of 2 papers in 2013, Carlen, Degond, and Wennberg, so 2 people are here that have done this, have created a swarming model that's very much like cat model in essence in terms of how it looks, but under the right rescaling, which we'll speak about in a moment, breaks chaoticity. So chaos doesn't always work. Can we find something that helps us? And that's the goal of this talk. Probably wasted 10 minutes on reaching this point. So let's go and speak about this particular model for me to try and introduce to you what I would suggest to not replace it, but complement chaos. So this is known as the choose the leader model or CL model. I'll continue to say CL model. And the idea is that it mimics very similar elements to Kat's model. It's a model where you have binary interaction in the sense that it's a pairwise collision process. You have n, don't think about particle, let's think about animals. And I urge you to think about herds of buffaloes in the African plain. And I'll try to explain why in a moment. And the setting is, in Kat's model, I have velocity, one-dimensional velocity. Here, the velocities of my animals are going to be planar velocity in a 2-dimensional plane, hence African plains. And they're going to be of length 1, which means that my process, whatever happens, the buffalo keeps on running, they do something, but they just change direction. It's more of an orientation type of collision than an actual collision. Now, much like Kat's model, there is some clock that represents the collision, which is modeled by a random Poisson stream. And when that clock chimes, you choose 2 random animals from your n animals. And once you have these 2, you choose one of them also in random, just to make it symmetric. And that buffalo that you've chosen to act looks at the other buffalo and says, oh, look at that buffalo, look at those legs, look at those hind, look at those back and those horns. I want to be you, oh buffalo leader, my heart. And they automatically change their velocity to be exactly plus minus the same velocity. They chose a leader and they follow it. Now, there's always going to be a bit of a wiggle room, right? If they're running, they're not going to align themselves exactly. Maybe they're like me, half blind, so they can overshoot. And in order to explain that, we're going to say they align themselves up to some error, and that error is going to be modeled by another random variable with density g to represent the deviation from my alignment. Now, because I'm talking about things on the plane and velocity of length 1, instead of writing vi, it will be more comfortable for me to write e to the power of I theta, where theta represents the deviation from just a fixed, some fixed axis. So if the first animal had angle theta, then my second animal is going to be the same theta plus minus delta theta, and that delta theta is going to be basically a random variable with a density g. And if I have that in mind, I can write the master equation, the equation for the evolution of the ensemble, and it looks exactly like the Katz model. And to begin with, this is the constant that appears in the Katz model. Lambda is the rate of the Poisson clock. And sorry, my state space, because I now move from v to this theta, then every theta is between minus pi and pi. For me, the minus pi and pi are the same, because I'm thinking about a circle. And my invariant measure is the basically uniform probability measure of this state space. So my evolution equation is going to be with these angles, with theta instead of v's. And you get the exact same flavor as in the Katz model. I have the gain term. How will I gain something? Post-collision, more like speaking to someone, I am gaining something that is the ensemble that I want to get. So for instance, this element here, I'm not using the laser because I personally can see it. What this means, it means that I integrated the jth velocity. So the jth animal chose the ith animal, and I replace where it lies by this g, by the distribution. I need to be theta I plus minus something that g tells me how much I deviated. This term here is exactly the converse where I chose to align to j, and that's why you get an extra half, and you get this minus f. Now this model, the way I described it, hopefully, make you think that it's not likely that I'm going to see chaos here, right? They're going to align themselves. They're going to really form some arrow and move through the plane, trampling everything. However, if you think about how I explained that chaos is created in the Katz model, we're going to have the exact same phenomena here. If I look at two animals, and I look really intently at these two animals, the scaling that I've done so far is such that at any given time, fixed time, or a unit time, there will be at least one meeting between two animals. But if I'm looking at two animals, and I'm increasing the amount of animals in the system, they're less likely to meet. So I'm still creating some chaos, even though my correlation pushed me to think that I'm going to be away from chaos. And the problem here is the time, one of the problem is the time scaling. So I need to rescale my time to make sure that when I'm looking at two animals, they will meet. So it's quite easy to believe me that I'll just scale the time by the number of animals. If I scale it by n, then any two animals have met, correlation would form, and I would expect to break chaoticity. And this is indeed what Eric, Bent, Pierre, and Pierre's postdoc, I think, have done, but they also did it, they showed that you also need to rescale your interaction somehow. It needs to become tighter. The alignment needs to become better and better with n. Now you might say this sounds unlikely, and I would argue this is actually very likely when you're thinking about animals, when you're thinking about humans. Let me give you an example. I would like to talk to Bertrand, because I love Bertrand. And we're a decent amount of people here, we're all chatting, so I'm aligning myself, I'm getting closer to him in order for him to hear me, even though I'm very loud, so I mean, this is probably enough. However, this door opens, flings open, slew of students gets in, they yap, so the number of people in the room increases. Consequently, I will align myself, I will get closer to Bertrand for him to hear me. So the more elements there is, the animal want to be closer by, because they're scared, because they're, I don't know, inspired, because they want to chat. So there is a reason for us to rescale our interaction as well as time. So if we do that and chaos break, would something replace it? So in case you didn't remember what chaoticity means, or I didn't explain, here's the formal definition. Please forget it's on a Polish space and all of that. I just want it to be very general. You have a family of density functions that represent the nth ensemble. You look at its kth elements, kth marginal, and you look at k elements from it. As you take n to infinity, this marginal converges to a tensorization of a given measure, which is why we say it's nu zero chaotic. However, again, going back to this herd, if I scale it properly, and now there are correlations are created, and the adherence becomes even more tight, what I expect is to basically them to form a line, an exact line. I mean, these are very thin buffaloes. That means to me that if I'm looking at any, here, if I told you, oh, here's one particle, and that's its profile, you would say any other particle has the same profile. But it's the same profile. If I look at them together, it's all smeared. If I'm in the order case, if I'm looking at this buffalo, if I tell you, here's one buffalo, it's going in that direction. Where are all the buffalo? All go in that direction. It's a deterministic pointwise things. In terms of a measure, the kth marginal is concentrated on the diagonal, because they're all moving as one. You know what one does, you know what everyone does. And that is my proposal for a definition of order. So if you give me a family of density functions, or it can be measures in general, and you tell me that it's nu zero ordered, what you're telling me is when I'm looking at the kth marginal, then as n goes to infinity, I choose, let's say, the first one. The first one has a profile nu zero, and everyone else completely align themselves to this profile, i.e. the second particle, the second animal, look at them, say, your theta is 1, my theta is 1. My life, your life. So I multiply by the delta measure concentrated of theta 1 for the second variable theta 2. And then the third animal look at the second animal and say, my life, your life, and so on and so forth. Now, I've chosen this definition just so it will look like a domino. It looks symmetric. Naturally, I can replace it by saying the first element has some distribution, and everyone else align themselves to this first element. So that would be what's written here, delta theta 1 of theta I. It's the same thing. I don't even have to choose theta 1. You can want to choose theta k, go for it. It doesn't matter because it's completely symmetric. Moreover, in many cases, it's nicer for me when I have an additive group on my setting, which I do on Rn, which I do on the circle. I'll write it as the delta measure concentrated of 0 of the difference between theta I and theta I plus 1, which speaks more of deviation, which is something that's easier for me to see. And just a small notation, notice that while in chaos, if my nu 0, my limit chaoticity, was a smooth density function, then the kth marginal would go to something smooth. It's tensorization. With order, you automatically generate singular measures, because you're going to be on the diagonal. It will never be absolutely continuous with respect to Lebesgue. And yet, if my limiting profile has some density, I'll kind of remove this d theta, d whatever. It's just a notation. But it's confusing between the two. Okay, so we have something that we may go to, and I told you that I need to rescale my interaction also. So rescaling time, I multiply by n just because that assures that at a fixed time 1, every 2 elements will meet, every 2 animals, but I also need to rescale my, my interaction. And the question is, how do I do that? If my interaction was on R instead of on the circle, then general rescaling, right? Replace x by x over epsilon, multiply by 1 over epsilon to conserve the mass, and you're done. But I can't do that as easily on the circle, so I cheat. I say, let's take something on R, do the normal rescaling, and now restrict it to minus pi pi. And I'll always choose g that's centered at 0 because I want the deviation to really be concentrated at 0, and I'll also choose g that doesn't notice between left and right, i.e. symmetric. And when I do that, when I take epsilon to be small enough, think about it, I'm compressing my density, so eventually minus pi, pi, r, it's the same. But to truly make it a probability density on the minus pi, pi, I just divide by the integration. This is the standard of this is the only type of concentration I'm going to speak about. I'm taking something on R, concentrating it normally, restricting it on the sphere. And the only technical thing is I'd like G to have a third moment. Okay, it's not too big. It's just for convenience. It doesn't even appear in the end. And this is the rescaled equation. So you see I have an extra n for the time, and the G was replaced by G epsilon n. Now, if I want to show you this chaos or order, I need to look at all my marginals. I need to find a BBGKY hierarchy. Okay, believe me, it's this. But I know it might look a lot, but it's actually fantastic, because it's a very simple model which allows me to do a lot. And it's because of its simplicity, I would say I get a huge dichotomy in the result. But unlike Bolt's in the Katz model, the kth marginal equation depends on the kth marginal and the kth minus 1 marginal. I don't go up, I go down. It's closed. I can solve it completely. If I look at the first marginal equation, I get, look at this equation, it's fantastic. It's a convolution, minus f, it's great. So that definitely says that I want to go to Fourier series. And when I do it, I get this solution in the Fourier coefficient. I see the Francois is going to stand up, so I'm going to speed up. And that indicates when I'm going to take n to infinity, I need to look at this Fourier transform of this G epsilon n. And when I do everything properly, the element that pops up is n epsilon n squared. I will need 2 more minutes. I warned you in the beginning, 28 minutes. Now, this n epsilon n squared really determines which phenomena is going to appear. And I claim I have 3 possible limits. If n epsilon n squared goes to 0, my spatial compression is stronger than my time compression. I create correlation faster. Consequently, you will get order appearing. If n epsilon n squared is 1, that's actually a diffusive limit. The scale of the time and space are exactly square of one another. That's exactly the case that Eric and Pierre dealt with, and there you break chaoticity. But I don't know what else about that. And you have the chance that n epsilon n squared goes to infinity, and that will be, the interaction is very weak, so you kind of lose it, but I'm not going to talk about that. And the main theorem I wanted to present is the following. If you start with any converging family of these marginals at time 0, then you evolve it along this choose the leader model. It will always converge for any time to a new family of function as n goes to infinity, which is given by this formula. And notice you start to generate delta functional. If I take this formula, so I took n to infinity, and now I ask what happens when time increases, I get that the limit as t goes to infinity is this, order. It doesn't matter how I started. I even started in a chaos state. In the end, if I wait long enough, I'm lying because I first take n to infinity and then t to infinity, but heuristically, if I have n big enough and t big enough, order is automatically created. Moreover, if I started with order, t disappears. It will remain order. The interaction was so strong that I reach my equilibrium and it's ordered. This is a propagation of order result, in a sense. And that was naturally in the case, sorry, when n epsilon n squared goes to 0. If n epsilon n was 1, as I said, Eric and Bent and Pierre showed that there is no chaos, but there is also no order. And you might ask yourself, well, you just told us in the previous slide that even if there's no order, when I take t to infinity, order pops up. Is this the case here as well? Well, I cannot tell you, I can tell you that the answer is no, but maybe something else pops up. So if you only look at the first marginal and the second marginal, if they converge at time 0, they will converge at time t. And then if I once again wait long enough, the limit of the first marginal limit is going to go to 1, diffusive limit. Everything smears out. I waited long enough, it diffused. But the second marginal goes to something that depends only on the difference between the angle, I speak of concentration, and my pride and joy, I managed to draw it. This is how it concentrates. So it seems quite concentrated at 0. It's not order, but maybe it leads to order with some errors. I don't know. I don't know what happens in higher order marginals. And that's a question for the future, maybe. And with that, I'll thank you for your attention.
Well, thank you very much for this beautiful talk. Question?
So, so you were discussing this CN model, which is like some kind of flocking model.
Mm-hmm.
And as I would say, in flocking models, usually the acceleration depends on the velocity on the macroscopic level, more or less.
So you're thinking of me moving from a microscopic system to this Liouville equation?
If you think, somehow like this. So in particular, this system is not Hamiltonian, right?
No, I don't think so.
Okay, so are there any like Hamiltonian system where you don't have propagation of chaos?
I don't know. The point is, though, this is slightly different approach because mean field limits, I've seen mean field limits coming from microscopic models, basically passing through the Liouville equation. But the Katz approach is more, we're starting with the master equation. And usually even the original Katz equation didn't conserve the momentum of the velocities. But you can still see, as long as you're going to have energy, something like an entropy naturally, you're going to lose Hamiltonian and things like that, right? So I don't know, it's a great question.
Yeah, I'm going to allow myself a question or remark. I mean, there's something that caught my attention when you show this order distribution. Of course, it reminds one of the diagonal embedding of a measure into n-fold Cartesian product.
Mm-hmm.
And so you know that if you take, for instance, if you take the x cross x, if you embed diagonally a measure into a product of two copies of the same space, this is the coupling that minimizes any Wasserstein distance.
Okay, yeah.
Right, and of course, if you on the other hand, if you take the coupling that is the tensor product, somehow it's in some sense the worst possible coupling to minimize the Wasserstein distance. So, question: is there a Wasserstein distance estimate for your integral in the style of what Tanaka did for the Boltzmann equation?
Not yet. It's definitely on the table. This result from September.
All right.
But you do remind me that there is this empirical measure criteria for chaoticity.
Yes.
So indeed, is there like a minimization problem that gives me the same time for order? Like what would be an appropriate empirical measure?
Yeah, because it seems that each step, you're sort of forcing. There's some kind of instant gradient descent at Wasserstein driving to some coupling that has this Wasserstein equal to 0. Again,
I mean, I'd be super interested in that.
I don't know if it's, any other question? Yes.
Sorry, I'll bring back the cat.
I was wondering, have you thought about also like in space?
In general, the answer would be no. Usually in this model, the randomness of the collision replaces the spatial variable, because the spatial variable cannot move the thing to collide, and when you have this clock, it replaces it. I think I don't know, I mean, there are better experts here, so please help me. Are there any mean field models that have both space and velocities in them, in this framework?
I mean, just
Yeah, I don't know, maybe it's nice to explore, but I don't know, sorry. I feel like my answers are very unsatisfactory today. Apologies.
Okay, perhaps the last question.
A partial answer to your question. Hammond and Rezekano did not with velocities, but with Brownian motions, and going to the Smolovsky equation. So they had a shrinking radius with lots of particles in it. So it's not quite velocities, but they did have a kind of space and a kind of local mean field.
That's interesting. I'll try to have a look and ask you for the reference because I didn't quite get it.
Yeah.
Brilliant. Thank you very much.
All right, so let's thank the speaker again.
Thank you.